Okay, I think we can get started slowly. So welcome everyone to this new seminar in the DEGAS webinar series. So today we have Gerald Mats giving a talk. It's a pleasure to welcome him here today. So Gerald received his PhD degree in electrical engineering and his habilitation degree for communication systems, both from the Vienna University of Technology. Was in 2000, 2004, respectively. Now he's a professor at that same institute. He also held visiting positions at Supélec in France, Toulouse, also in France, and then ETH in Zurich as well. Published hundreds of different scientific articles. Maybe also worth mentioning is that he co-edited a book on wireless communications over rapidly time-varying channels, which was a hot topic like a decade ago. That's also where his research interests are in wireless communications, but then more recently also towards network processing and graph signal processing. Also related to his activities for IEEE, so he was a member in two technical committees of the IEEE Signal Processing Society, also associate editor of many different IEEE journals, as well as the EuroSIP Signal Processing Journal. Currently, he's the deputy editor-in-chief of the Transactions on Signal Processing of the IEEE. In terms of conferences, he served as the general chair of Asilomar 2019, was also technical program chair of Asilomar 2016 and USIPCO 24. Right? And he's also a fellow of the IEEE. So, Gerald, it's a pleasure to have you here. So we're looking forward to your presentation. So thanks again.
Thanks a lot, Gerard, for the kind introduction, and thanks to the organizers for inviting me. It's a pleasure to be here and to report a little bit on some of the things we have been doing recently in this area of graph signal processing, let's say. And so the title of the talk is Graphs from Multiple Data Dichotomies. You will see in a second what this is about. Let me just mention that this is joint work with my PhD student, Thomas Dietrich, who just recently graduated, and Claudio Verrado, who was a visitor with us, who is now back in Udine in Italy. So let me just start with clarifying the terminology here. Dichotomy is maybe a little bit of an unusual word. This is coming from Greek, dika et tome, meaning that you cut sets into two, and usually the split into these joint parts is supposed to obtain parts that are somehow opposite to each other, right? So here you see this sketch with green and red. So you may think, for instance, left, right? That would be an example for such a dichotomy. And there's a generalization of this, polychotomies, which is many parts, right? Which I'm not going to use a lot here. I'm going to prefer multiple dichotomies because actually the split into many parts that we were interested in is kind of a joint multiple partition in binary parts. And I hope at the end you will see how that works out. So just from these definitions, there is already a connection to classification and clustering that pops up, and indeed I'm going to talk about this also towards the end. So let me start with motivating this with a very simple toy example, just to get us going and give you kind of a preview of what we are about to do. Let's say you got a couple of data points. In this case here, there's 16 points that are given in 2 dimensions. Here you have the corresponding coordinates. And in data science, the idea is that we try to understand the structure of the data set, right? We want to figure out what kind of relations we got with the data at hand. And okay, this is a series of talks on graph signal processing. So graphs is the tool of choice. And the classical approach would be to construct a graph based on similarity relations. So essentially you would look at the distance of the points, and whenever the distance is small, you think that the data entities are somehow similar. And this you capture by putting edges in a graph, right? And I'm going to call these kind of graphs unsigned, because here we just have positive edges that indicate that certain data points are similarity. And this is telling us already quite a little about the underlying data set. However, there is aspects of the data set that are not evident in this representation with an unsigned graph. So if I go back here to the data set itself, you see that you may think that there's actually a couple of point clouds here that we can think of as separate groups or communities, if you like, right? And this kind of relationship is not that obvious in the unsigned graph. Specifically, points lying diametral to each other are not connected in the unsigned graph. So there is information that's which is not conveyed by this kind of construction. So that's why people, and this goes back already a while, have started to think of complementing the unsigned graphs where you just have positive edges with negative edges. And the way this works here is that what I did here is that I first centered the data. So we've got now a coordinate system where here in the middle, you can think of this as the origin. And then you realize there's actually data points that lie on opposite ends. For instance, this first point here, you see this has a coordinate of 0.8, 1.5. So that's this guy here. And there's another point down here, which has minus 0.7, minus 1.6. So that should be this guy here, I guess. And those, in terms of magnitude, have more or less the same coordinates, but they lie on opposite ends of the spectrum. So they are diametral or the opposite of each other. And these kind of relationships we can capture with signed graphs. So here what we do is on top of the positive edges that capture similar data points, we put negative edges, which here are now shown in red. And those are the ones that connect points that have diametral or opposite coordinates, right? So this is already kind of strengthening the insights that we can get. And what we did recently is we took this a little bit further, because also here, it's not the complete relationships that are represented by this graph. So for instance, there's points that have the same horizontal coordinate, like these guys here, for instance, almost, but lie on opposite ends with regard to the vertical coordinate, right? So they're neither similar, nor are they diametral, but they agree in the first coordinate and disagree in the second coordinate. And this motivated us to introduce what we call signature graphs. And those are graphs that can capture now multiple dichotomies. Okay, so signed graphs, one dichotomy, signature graphs, we have multiple dichotomies. We have now 4 kinds of edges: green ones that capture similarity, red ones that capture opposite behavior, diametral behavior, and then there is now this magenta and yellow edges on top, where magenta means that they have similar horizontal coordinates but opposite vertical coordinates, and for yellow it's just the other way around. Okay, so this is where this is going. And so let me start with the case of one dichotomy, which amounts to using signed graphs, and dig a little bit deeper on how things work out there. So as I said before, here we got positive and negative edges, and those can model all kinds of different relationships. For instance, we could have as I said before, similarity, dissimilarity relationships. If you think social networks, you might have relation between players that trust or distrust each other. So as a matter of fact, here, there's a couple of signed graphs that illustrate this. These are real data sets. What you see here, that's a signed graph constructed from data on the Bitcoin Alpha trading platform, where there is, in this case here, 1,000 users picked. And they trade with each other, but some trust each other and others don't trust each other. And this distrust relation is captured by the green and the red positive and negative edges, respectively. Probably the oldest one is this thing here. That's the so-called friend-foe network for highland tribes in Guinea. Where the relationships is that some tribes are friends of each other, others fight each other, so they have foe relationships, and this also is captured by positive and negative edges. More recently, here you see a network that's constructed for the E. coli bacterium. So this is a gene transcription network where each of the vertices corresponds to a regulon. So that's a group of genes, and those may either activate or inhibit each other in the transcription process. And this activation and inhibition, again, can be captured by positive and negative edges. So this just kind of sets the stage a little bit for signed graphs. So let's make this a little bit more precise mathematically as well. The way we think about signed graphs is as a collection of a vertex set, which without loss of generality, I'm going to assume is just the numbers from 1 to n integers, which we can always achieve by just relabeling the vertices. And the relationships between the vertices are captured in terms of a matrix W. So this is a weighted adjacency matrix, or an edge weight matrix, if you like, where for signed graphs, the novel aspect here is that those can go negative, right? So usually in unsigned, you would just have either 0 or positive weights indicating the presence of an edge. But in signed graphs, we can also have negative edge weights, which indicate that there is a relationship, but the nodes have antipodal behavior. They are diametral to each other. Simple 4-node example here to the right. For nodes, you see there's 2 green positive edges, 2 red negative edges, which give rise to the weighted adjacency matrix that you see over here with the corresponding entries. Now, what's going to be useful is actually to split for these positive and negative edges the sign and the magnitude information from each other. So we represent the weights as the product of the magnitude, which I denote with the tilde, and the sign, which I denote by S. Okay, and the sign can be now either positive or negative, so this can have only 2 values. The magnitude can be any positive or non-negative number. If it's 0, of course, it means that there is no edge at all between those vertices. So what can we say about these kind of graphs? There's lots of tools that can be generalized from the case of unsigned graphs. Specifically, we can come up with generalized notions of similarity and smoothness. And so one way to go for that is to define a generalized version of the Laplacian matrix. So this looks pretty similar to what we have in the unsigned case. It's a diagonal matrix consisting of the degrees minus the edge weight matrix. Note that there's 2 things that are different here. First of all, the edge weight matrix here can have negative entries, which means that in the Laplacian, this will actually give rise to a positive off-diagonal element. And the other difference is that in the computation of the degrees, we actually take the sum of the magnitude of the weights. Okay, so for the degrees, we don't care whether it's a negative edge or not. Everything contributes equally to the weighted degree of the corresponding vertex. And this definition has the advantage that if you look then in the quadratic form with that signed Laplacian, you get a representation that's similar that you may know from the unsigned case, right? Like shown here, where you have a sum over all vertex pairs with the corresponding weight edge, edge weight, but here it's just the magnitude that matters in the weighting process. And then you have what in the unsigned case is the square difference. So there you would just have xi minus xj. In the signed case, this is now modified by actually, as a result of using the magnitude here, in the way that there is the sign of the edge that kicks in the difference building process. So actually for negative edges, it's not the difference, but it's the sum of xi and xj that matters. And if instead of the square here, you just use the magnitude, you end up with a generalization of total variation, slightly different metric that for some purposes has advantages sometimes. But at the end of the day, both metrics kind of measure the amount of variation that the signal, the vector x, has on the graph. And so it's just by looking at this, what you can see is that in order for both of those quantities to be small, what you require is that if you have a positive edge, then xi should be equal to xj in order for the difference to be small. So this is what we know from the unsigned case. But for negative edges, actually, we want to have the opposite behavior. If there's a negative edge, then actually the value at node I should be the negative of the value at node J. And this will give us a different notion of smoothness here on signed graphs. Now, one of the concepts that's extremely powerful in signed graphs is the notion of balancedness. And so this goes back actually a long time. Harari was the pioneer on in signed graphs. He was analyzing social networks, and essentially the reasoning was that they said, okay, if I'm having a faux relation with somebody, and that person has a faux relation with somebody else, then the foe of my foe should be my friend, right? That's kind of the reasoning that led to this notion of balancedness. And mathematically, you can capture this by looking at your signed graph. And if there is cycles, what you require is that any cycle must have an even number of negative edges. So you must not have odd number of edges along any cycle. Okay. So here for this toy graph, again, green is positive edges, red is negative edges. You see there's 3 cycles, this guy here, the other one over here, and then the large cycle traversing all the vertices. And if you count, you see that for all cycles, there is exactly 2 negative edges, which is even. So this is indeed a balanced graph according to that definition. And mathematically, this is usually captured by multiplying up the signs of all the edges along the graph, right? So here you would have +1 times -1 times +1 times -1, which would be equal to 1, indicating an even number of negative edges along these cycles. Okay, and this you would have to need to check for all the cycles in the graph, which here is simple, of course, but for larger graphs, it's a little bit more elaborate. Fortunately, there is alternative equivalent conditions for balancedness, some of which are easier to check. And the first equivalent condition, which is interesting specifically from a classification perspective, is the fact that for balanced graphs, it's possible to split the vertex set into 2 disjoint parts. And the split is such that if nodes belong to the same part, they are necessarily connected by positive edges, if there is an edge at all. Whereas if they belong to different parts, then the connection must be negative. Okay, and so here you see this indicated for our toy graph. The top nodes are the first vertex group. Below this is the second group of nodes. And indeed, all edges within V1 and within V2 are positive, whereas all edges that go from V1 to V2 are all negative, as you see here. Okay, and obtaining these groups is actually simple. All that you need to do is you just need to drop all the negative edges, right? So if you remove those, actually you get the split where the remaining components are exactly the 2 groups that you're interested in. Now this can be taken further to a condition which is related to what's known as sign switching. Now in sign switching, what you do is you try to find a vector, which is again binary valued, -1 +1, which assigns either +1 or -1 to each node. And the assignment should be such that if you multiply your weight matrix from left and right, more or less with that sign switching vector, what you get is the unsigned version of the weight matrix. So all the negative edges will be removed by doing this sign switching. Okay, so if you write that out in scalar, what you see is that actually each row and column will be multiplied with the corresponding element of the sign switching vector. And this is equivalent actually to requiring that the signs on the edges must be the products of the corresponding elements of the switching vector. So again, here is the illustration for our toy graph. You see what I did here is I put +1s here on the top nodes and -1s on the bottom nodes. And the switching is such that if you have 2 vertices that are connected, then if the switching vector has identical elements, you leave the edge unchanged. Whereas if the elements of the switch vector are different, like here for those 2 guys, then you will switch the sign of the edge, right? So these two will switch this to a positive edge. Those two guys will switch this one. Those two will switch that one. And you see that there's no switch occurring in the top and in the bottom vertices because they all have the same value for the switching vector. And we'll see how this will be useful in a while. As it happens, an alternative perspective is that actually, if now you take the sign switching vector and insert those that into our smoothness metrics, either the Laplacian or the total variation, it turns out that the result is 0, which means that the sign switching vector is actually perfectly smooth on our signed graph. Perfectly smooth in the sense that along positive edges you have identical values. Along negative edges, you have opposite values in your signal. So this gives us several conditions for balancedness. Now, let me show 2 application examples for signed graphs that we were looking at to illustrate possible advantages of this. The first one was a signal reconstruction problem where what you're given is noisy samples of a signal. So what you're interested in is actually the signal S, and you get samples of that signal on a particular sampling set. So for a certain index set S, and we're going to assume that for all the remaining indices, the observation is 0 for simplicity. And the goal is to reconstruct the signal itself for all indices, right? So even for the non-observed locations, of course, you want to also suppress the noise. And if you have an underlying graphical model, one of the things to go for is to do Laplacian regression, which means that you require the signal to be smooth on the graph. So this is kind of a band limitation model, if you like, on the graph. And then there's the data fidelity term, which means that the samples, that the signal that you reconstruct should be consistent with the measurements that you have on the sampling set. Now, this is a quadratic problem in the signal S, which can be solved by a system of linear equations that I'm not going to dig into deeper. It's a sparse system of equations, so it's pretty efficient to solve. And so, of course, what you need for that is you also need the graph topology. And in the examples that I'm going to show is that what we're assuming is that you have seen examples of the signals that you tried to reconstruct before, and you have learned the graph from those examples. And the learning I'll talk about a little bit later. Here, I just want to show the reconstruction results for a signal model that looks like this. So here you have an example signal. So you see this is pretty smoothly evolving, but there's a structure to it, which is actually that there is odd symmetry, right? Which means that the second half of the signal is actually the mirror flipped version with sign change of the first portion of the signal, which the algorithm does not know, right? So what we did is we presented a graph learning scheme with examples of these types of signals, constructed graphs that you see over here. I'll comment on those later. And then we use those graphs to do the reconstruction. Okay, so let's look at the learned graph. So what you see here is actually, again, the signed graph with positive edges for neighboring vertices. So this captures the smoothness. But what this signed graph was able to learn is also the fact that these samples here actually have more or less the same amplitude, but opposite sign, right? And these are actually the vertical red lines that you see here in the visualization of this signed graph. Whereas if you go for unsigned, this information cannot be extracted, right? And okay, you still learn somehow smoothness relations between neighboring samples, but the odd structure of the signal, the odd symmetric structure, cannot be captured here. And so if you use those graphs then to do the reconstruction, for instance, from noisy samples that are shown here, then with the signed graph, you get the reconstruction shown on top. This is the unsigned reconstruction. And you see that the unsigned is much worse because it's not able to actually fill in, to paint in everything that's missing here in the second half of the signal. And actually, if you look at this from a systematic perspective, running lots of simulations, Monte Carlo simulations with lots of different signals, and look at this at the mean square error that you obtain as a function of the sampling rate. So here in the example, the sampling rate is 8 out of 32 samples, so 1/4. But if you change the sampling rate, then you get a behavior that's shown here. Dashed is unsigned. The solid line is the signed graph. These are two SNRs, 24 and 32 dB at two different colors. And you see that there's a substantial advantage at both SNRs for using signed graphs. So typically there is an advantage of around 7 dB in terms of reconstruction error. If you look at this from a different perspective, if you want to achieve a particular reconstruction error, then what these graphs are saying that for unsigned graphs, you will require roughly twice as many samples as for signed graphs. So there is things to be gained by admitting negative edges and using signed graphs. Similar kind of advantages we saw in clustering. Here there's a simple example, a classical data set used in clustering, the so-called two-moon model, where essentially you have two half moons looking more or less something like this, and the data points are actually scattered around these two half moons, and then you want to separate and identify the points that belong to either of the two half moons. Okay. And so in this case, we were using total variation as our metric for the clustering, because this has certain advantages in clustering problems. So Z would be the cluster label. This is either +1 or -1 for one of the two clusters. And the set C here is actually modeling a training set. So this is a semi-supervised setup. There's 2 points actually for which the labels are known, and then we try to classify all the rest. Okay, and so on the right-hand side you see the unsigned approach, where you just have positive edges, and the problem here is that the two half moons actually can pretty much grow into each other, and then instead of two half moons, what you see is more or less an S-shaped thing, where it becomes pretty arbitrary of where you cut through in terms of achieving the clustering, right? So here the cut happened at this point in terms of minimizing the total variation, and obvious there's a large number of points that has been misclassified. And this cannot happen in the signed case, because here for those points, you see that there's all kinds of negative edges going across, which kind of clarify that these points, that the proper way to the proper point to cut is actually somewhere here between the two moons. And again, if you do systematic experiments for this, Monte Carlo runs for different graph realizations and different, then the behavior that you get is shown here. This is misclassification rate, number of incorrect nodes, incorrectly classified nodes. What you see here is the complementary cumulative distribution function, and this is on a doubly logarithmic scale. Yellow would be the signed approach, red is the unsigned, and the blue one here was just for reference, a frequently used method, which is just constructing a K and N graph and minimizing total variation on that, which here performs worst of all the three approaches. Again, you see that there is quite an advantage here between signed and unsigned. So not only is the average misclassification rate much smaller than for the signed case, for the unsigned case, but also the stability, right? So you see the variance of the misclassification, and this was fluctuating very little, whereas in the unsigned case, you have much more fluctuation. As a matter of fact, in these cases, there can be even catastrophic events where all the nodes are basically assigned to one class only. And then you end up with these worst case things here, where you have 500 nodes misclassified if you run into a bad realization of the data set. So from here, let's move to multiple dichotomies, right? And the motivation that I also tried to give at the beginning is that you may have data sets where you don't have similar or opposite behavior in all dimensions. So it's just partial agreement or disagreement that you see in the data set. across different coordinates or different dimensions. I got a data set here to motivate this. This is geometrical parameters of wheat seeds. So the people there took X-ray pictures of wheat, of the little kernels, right? And they extracted parameters like perimeter, width, length, asymmetry, and so on and so forth. And if you project that into 2 dimensions, you get the representation like shown here. And there's actually 3 varieties, 3 types of wheats that you see here. There's Rosa, Kama, and Canadian. And you see that for the same variety, actually, you get pretty similar locations of the measurements. And interestingly, for the Rosa and Canadian variety, you have antipodal behavior, right? So those are diametral to each other. But the third variety, Karma, is neither similar to one of the other 2, nor is it antipodal, right? So it agrees in the first dimension with Rosa, but it agrees on the second dimension with Canadian. And this cannot be captured with a signed graph, right? So here, we'd like to have multiple dimensions to capture all these relationships. And that's exactly what signature graphs are about. Okay, so we now think of those n objects as living in m dimensions. And that means that in order to capture the multiple relationships, one weight will not suffice anymore in the construction of the graph. So what we use is an edge weight tensor. That's not an n by n matrix now, but actually for any pair of vertices, you assign a vector, if you like, of length m matched to the dimensions that you have in the problem. Now, this blows up the dimensionality quite substantially. And what we found is that it's useful both from a theoretical perspective and from a computational perspective to impose a structural constraint, which is that if you look at the weight, so this is now Wij with an additional index m, that's the dimensionality index. And what you require is that, again, this can be split into magnitude and sign, but the magnitude information is independent of the dimensionality index m, okay? And we'll see how this becomes important a little bit later, right? So the sign can be different on the layers, but the magnitude must be the same on all dimensions. And there's 2 interpretations we got for these graphs. The first one is that you think of them as ordinary graphs where the edges have weights that are vector valued. Okay, so you have vectors Wij, and due to our constraint, this is actually the product of the magnitude with a vector containing the signs. And those signs preferably we arrange into a diagonal matrix Sij. And these are actually objects that exist in the mathematics literature and physics literature, and those are called signature matrix. So those are actually the name givers for the graphs as well. So I picked a simple example here to illustrate what's going on. This is a setup where there's 2 dimensions. It's motivated by looking at a political landscape where the players can be either left or right leaning in the first dimension. And in the second dimension, they're either libertarian or authoritarian. Okay. And you see there's 8 players in here. And for some of them, like for instance, nodes 5 and 1, they are connected by an edge with a vector valued weight +1, So they agree in both dimensions. They're both left authoritarian, right? 2 and 4 are connected by an edge with -1, So they're totally opposites of each other. 2 is right authoritarian, 4 is left libertarian, right? So disagreement in both coordinates. And then there's the other 2 combinations that you can have. You can have 2 players that are both right-leaning, 6 and 7, but one of them is libertarian, the other one is authoritarian. Or 7 and 8, for instance, are both libertarian, so they agree in the second coordinate, but one is left, the other is right, so there's disagreement in the first dimension. It turns out that an alternative view on these signature graphs is by splitting the weight tensor across the dimension coordinate m, right? So in that case, each slice is actually will give you as one signed graph, which we denote by a G with superscript m. Okay, so we get m of those. And we can characterize their weights as well. This is just the structure constraint that says that the magnitude is the same on all for all slices, but the sign matrix can be different on any slice. And this we can think of alternatively also as a multi-layer graph, right? So it's one graph with multiple layers corresponding to the dimensions. But there's a couple of things that are especially here, which is first, there's no edges between distinct layers. And all the layers must have identical edge set. That's the restriction, that all the weights are the same on all the layers. So if there is an edge, the magnitude is larger than 0. This must be true for all the layers. Okay. Here we'll see that perspective for the example that I gave before, right? So if you split the first dimension and the second dimension here from the weight vectors, then what you get is here, this as the graph for the first layer, and this is the graph for the second layer. So this is basically the left-right dichotomy. This here is the libertarian-authoritarian dichotomy in the second dimension. And here you have just edges with +1 and -1 weights, but you have got two of those. Now, smoothness carries over pretty straightforwardly. Essentially, you can come up with a Laplacian form which just adds Laplacians for all layers. And that, of course, means that the graph signals that you got are now living in n times n dimensional space. So we have one graph signal for each dimension, if you like. And the main difference that this causes is that in the usual representation of the Laplacian, in case instead of just having the magnitude square of the difference or the sum, what you get is a norm squared of this kind of weighted difference where the signature matrices kick in. Okay. And in order for this to be small, to have signals that are smooth on the signature graph, what we require is that the signals on node I and node J are related by the signature matrix, which means that some of them should be just identical if the sign is positive. Others should have antipodal behavior if the corresponding sign is negative. And this is all captured simultaneously by the signature matrix. Now, I said for signed matrices, for signed graphs, balancedness is a big thing. And this is actually also true for signature graphs. So there's a generalization that's possible. And specifically, the constraint that the product of the signs along any cycle must be equal to 1 that we had in signed graphs, we can generalize to signature graphs by requiring that the product of the signature matrices along any cycle must be equal to the identity matrix, which is the generalization of the one, right? So this is a condition that you can check, and the graph that I gave as an example here with the political landscape happens to be indeed balanced. So there's two cycles that I picked out here, one going from node 1 to 2 and then to 3 and then back to 1. And if you extract the edge weight vectors for those for that cycle, here you have the product of the corresponding signature matrices, and this is indeed equal to the identity. And the same for any other cycle here. There's a little bit longer one, but the check is the same. Okay. Now, again, enumerating all the cycles might be a little bit undesired. And fortunately, we were able to extend the insights that exist for signed matrices to this multidimensional setting. So there's again actually equivalent conditions for balanced signature graphs that are shown here. And the crucial one maybe is actually the second one, which says that if the signature graph is balanced, what it implies actually is that all layers by themselves must be balanced signed graphs. And this then has further implications. So in that case, what you can show is that if you look at all the layers, the weights on all the layers can be related by sign switches as well. And you find a matrix like in the signed case for which the Laplacian becomes 0. So this is perfectly smooth on the signature graph. And you can also come up with a node split. So here, this is captured in terms of a labeling, a node labeling, which says that if two nodes receive the same label, then they must be connected by a signature matrix that's the identity matrix. And if the signature is the non-identity, then the labels must be different. Okay. And the thing maybe to emphasize here is that the label is a mapping from the vertices to the set 1 to k. And what we need actually here is that k is less than 2 to the m, right? So the number of labels that we can give in a balanced graph is allowed to grow exponentially in the dimension. And this is a huge advantage, as we're going to see in the clustering examples that I'm going to show. So in the interest of time, maybe let me skip the proof of this. It's pretty similar in spirit to the signed case, and rather let me talk now at this point about how the learning works. And the idea is that we want to capture or identify the graph topology of signature graphs and signed graphs from data. We assume that we're given L data matrices. In the worst case, L could be equal to 1, but you can have multiple of those. And so essentially, that means that for each node I, the ELF measurement gives you a per node measurement vector, right, across all the dimensions, right? So this is an m-dimensional vector that you get for each vertex, okay? And the idea, of course, is that you want to identify vertices that have similar or partially similar elements to construct the graph. Accordingly, constructing the graph means, of course, to finding the magnitudes and the signature matrices in order to have the full weight tensor equivalently. And we use the common rationale that lots of people have been looking at also for unsigned graphs to try to learn a graph such that the data that we have is smooth on the graph. And this is equivalent, of course, to saying that what we want to have is that specifically with regard to the signatures should be chosen such that the relation between the measurements is consistent with the signatures. And this can be formulated as an optimization problem where the smoothness we capture in terms of the Laplacian. It's just here that the weights and the measurements are made explicit. There's a regularization term here, which usually is chosen to be the Frobenius norm of the weights that allows us to control the sparsity of the graph. And then there is additional constraints. For the magnitudes, the minimum constraint set is that they must be non-negative. We want to have no loop, so the diagonals must be 0, and we need the normalization to prevent that the solution where all weights go 0, right? So this is just this normalization here at the end. But you could have additional constraints that you can incorporate. You can have constraints on the degrees, on the support of the weight matrix, and so on and so forth. And the important thing to observe now is that the structural assumption that we were making with regard to signature graphs allows us actually to decouple that problem into two subproblems, where one is with regard to choosing the signatures, and then we're just left with learning the weight magnitudes, which turns out to be an ordinary graph learning problem for unsigned graphs. And so the trick is actually to work out to observe that in the Laplacian, the term that involves the signatures here are isolated, and there's just one term for any pair of I and j, right? So we can actually choose the Sij's for any pair of measurements xi and xj. If you do that, this is the corresponding optimization problem. And intuitively, what's happening is that you're going to look at the similarity, at the correlation of the measurement at node I and the measurement at node j. And if that correlation is positive, then you assign a positive sign. If the correlation is negative, you assign a negative sign to your signature matrix. So with that, we can construct all the required signs. So we got the optimum signature matrices. We can plug those back in over here, and then we are left with optimizing the weight magnitudes. And for those, the regularization and the constraints, of course, need to be carried along, but that's just ordinary unsigned graph learning for which plenty of proposals have been made. This is an illustration of how this plays out. So it's pretty similar in terms of structure to the examples that I was showing before. These are 4 spheres, or L6 spheres actually. So if you think squares with rounded corners in 2-dimensional spaces with 640 points in total. And you see the unsigned graph works well in identifying similarity relations between the elements of the individual L6 spheres. The signed graph also learns that the opposite behaviors indicated by the red edges. And with the signature graph in 2 dimensions, we also are able to identify horizontal and vertical similarities. So pretty much what I was explaining in the motivating example at the very beginning. So we get a much more insightful representation, data representation than with the other types of graphs. So let me say a few words about how this can be used then for clustering. And again, the key insight, maybe without going too much into the details, is actually that the structural constraint that we were making for signature graphs, same edge set on all the layers, allows to decouple the global clustering problems into layer-wise clustering problems, right? So instead of clustering the full signature graph, what you can do is actually you can cluster each layer separately, and on each layer it's just a binary clustering problem that you're left with. Okay, and the binary labels that you obtain in each of the layers together give you then a characterization of the labels for the individual clusters on the global graph. Okay, so we looked at this for spectral clustering, in which case this boils down more or less just to identifying the first eigenvector in an unsupervised manner. If you do that, you'll find that for the same model that I was showing before, the misclassification rates are much better with signature graphs than with the other 2 types of constructions. So here, this is misclassification rate versus SNR. So SNR is basically a metric of how scattered the points are around these L6 spheres, right? So smaller SNR means that the spread is larger, so the spheres will start to overlap stronger. And yellow is signature, red is signed, and the blue dotted is the unsigned approach. So it's all learning the graph from the data set and then running spectral clustering. And you see that there is huge advantages by 5 to 10 dBs for all kinds of scenarios. So this here would be 4 clusters in 2 dimensions. So that's pretty much what you see here for the graphs that have been learned. But even if you go higher dimensional, if you go through 3-dimensional space, in which case you can have 8 clusters, right? Because remember, we can have exponential growth in dimensionality. The performance of the signature approach is pretty much unaffected by that. It still works plenty fine, way better than the other 2 versions. Now, to close this up, the most recent thing we were doing is we were thinking, okay, in this approach, the strategy is always first take the data, learn the graph, and then you have to do the clustering on the graph that's been learned. And in the multi-layer setup, usually what's being done is that there is even a layer aggregation step in between. So you learn the layers, then you aggregate the layers, then you do the clustering. So lots of intermediate steps. And what we were thinking is to try to learn directly a balanced graph that's matched best to the data, because for balanced graphs, what we need to do, the clustering comes for free, basically. We just need to drop all edges that are negative, right? And so we came up with a learning scheme that's similar to what we had before, except we impose a balancedness constraint on top of that. And this can be shown just to mean that the sign matrices that we have on all the layers must have rank 1. Okay, so they have 1s on the diagonal. That's just the ±1 values. positive semi-definite, and rank 1. And as soon as you write this out, what you'll find, and I'm skipping the details here in the interest of time, is that at the end of the day, you obtain a semi-definite program for the sign updates, right? So the sign update becomes a little bit more involved because there's not the structural constraint, but fortunately, it can be still phrased as a semi-definite program if we relax this rank 1 constraint. So this is a pretty standard approach that has been used all over the place, communications and so on, to deal with these kind of problems, okay? And so this affects the sign update, and then what we do is basically we just alternatingly optimize the weights and the sign matrices, and we saw in the simulations that 2 or 3 iterations of this are usually sufficient to construct a balanced graph to converge to a solution, and this actually has substantial advantages. So here, let me show you just again for an example for this balanced learning approach in the signed case. So one-dimensional. This is again 2 moon. We got on the left here 300 vertices. On the right, this is 500 vertices. The lower plots are for total variation clustering. And this is actually semi-supervised. So one node actually has a known label, and then you perform clustering using total variation. And this has pretty okay accuracy, so 94% roughly here for 300 nodes. If you have more nodes, you see things become denser, then the accuracy goes down a little bit. But if you directly learn a balanced sign graph and drop the negative edges, what you get is an average accuracy here, which is 97.7, and this is basically independent of the number of nodes, and it's much more stable. So see again, the variance is pretty small as compared to the variability that you see with the other types of constructions. And so to the final thing to show that I got here is a real data set to which we applied this balanced learning strategy. This is voting data from the US Supreme Court in the year 2000-2001. And, you know, there's 9 justices on the US Supreme Court, which are known, some of them to be liberals, other conservatives. So at that time, actually, there were 4 liberal justices and 5 conservatives. But as it happens, if you look at the data set, and this you can only figure out if you learn a signature graph, is that there is actually more than these 2 clusters. There's actually 3 clusters. So the node color here indicates cluster affiliation. So here you got your 4 liberals, but for the conservatives, actually there was a split between O'Connor and Kennedy and the other 3 guys, which are kind of the hardcore conservatives, if you like, right? And this separation was only possible to discover by looking at the 2-dimensional representation of the data set and learning 2 layers of the corresponding signature graph. So here actually you have the 2 layers. Here you see basically the liberal conservative split, but there is another split for certain votes where O'Connor and Kennedy actually went along with the liberals and were not in accordance with the 3 conservatives up here. And all this information is basically impossible to extract if you just use a baseline unsigned graph construction. So of course you get a graph, but even the labeling is incorrect. And so the thing that I should point out here is that for the signature graph construction, the number of clusters was not prescribed. It's 2 layers. So anything from 1 to 4 clusters could have been possible, right? So it did not exhaust all 4. The 4th label basically went unused because that's what best matches with the data. So with that, I'd like to conclude. I hope I'm not walking through the conclusions here. Just let me say that I hope I've convinced you that for certain types of data sets, this approach of using signed graphs and signature graphs are pretty advantageous if you have these single or multiple dichotomies present in the structure of the data set. And this is helpful for all kinds of things, specifically also for clustering. So with that, I'll conclude. Thanks for listening.
Thanks, Gerald, for the nice presentation. Very interesting. Okay, any questions from the audience? So there was one in the chat, but it was already answered later on in your talk.
Yeah. Okay. Yeah.
So maybe I can start off. Yeah. So when you do this topology identification, and like in this last example, for instance,
Yeah.
what exactly is the data then that you're using? Because I guess you kind
yeah.
of need to know how many layers you have, right? Because your data is related to that.
Yeah. So in that case, actually, the data was that this was a collection of 20 votes by the judges, right? So the data matrix in this case is essentially 9 by 20. So it's a small scale example, of course, right? And then essentially the decision is into which dimensionality you want to go, right? And the thing is that since there's just 9 judges, I would not have expected that there is more than 4 clusters, which means that in that case, 2 dimensions will be sufficient. And so what we did is actually we projected the 20-dimensional data set, 20 votes, into the 2 dominant components.
Okay.
So essentially, this is principal component analysis into 2 dimensions, and then with that, that's what you feed to the learning scheme, right?
So you have 9 by 2 matrices, and you have a bunch of those matrices then, which are related to voting.
Yeah, exactly.
Okay, voting results. Okay.
Yeah. Except for the unsigned graph, I should add, for that we used the full data set, right? So there was no principal component stage in advance. You just go with similarity across all votes. And interestingly, still in that case, in spite of the absence of the pre-processing, the graph construction still does not have the expressive power as the other.
Right. But it's hard then to interpret the data in the different layers in a way, right? So, okay, they are like main components, but.
So yeah, okay. In terms of what the real world meaning is, then you're saying.
Yeah, right.
Yeah. So for that, I think you would have to need exactly in what the combinations are, because the votes are characterized. So there is votes that deal with abortion and liberation of cannabis consumption and so on and so forth. So I think probably that there's some that will be grouped together actually in these layers.
Yeah. But that's crucial, like for your methods, right? That you have data. Let's say you have that your vector. Basically, every node has a vector of data, right? Like you said, and it should be, the size should be equal to the number of layers that you have.
Yeah. Right? Yeah. So if you don't have that, that's why in that case you need a pre-processing step.
Yeah. Okay.
So as long, of course, as the construction is from data, right? There is other situations where trust and distrust relations, so where the construction is different. And then the clustering, of course, you can still apply, but for the graph construction, you're right with what you said. Yeah.
Okay. Clear. Yeah. Thanks. There's another question in the chat. Gerik, yeah, maybe if you want, you can also unmute yourself. Otherwise, I can read it.
Yes, I can explain if you want.
Yeah, go ahead, Gerik.
Yes, so you talked about PCA. And would it be possible to value more like the first dimension of the PCA and then do the clustering, so that the clustering is based on also the importance that you give to, I don't know, arbitrary dimension in signature networks?
So we didn't do that, but it makes perfectly sense to me, because I mean the pre-processing stage, of course, is a little bit arbitrary, right? Of course, I mean, you can do principal components, you can do multidimensional scaling or any other projection step that you prefer. And if you have domain knowledge that tells you to emphasize certain aspects of the data set stronger, I guess that could be indeed incorporated in that pre-processing step. Yeah. So okay. I'm pretty confident that that's feasible, but I have to say we didn't do it up to this point.
Okay, thank you.
Any other questions?
I have a question, if I can.
Oh, yeah, no, maybe you're first.
Okay, thank you. Thank you for this very interesting work. I would be more than interested to read a bit more the manuscript, basically. But so there is a point that I'm sure that you mentioned it in the talk, but it's not very clear to me right now. Do you have any constraints between the layers, imposing some orthogonality or some type of?
Yeah.
Is there?
So, yeah, the constraint that we had is not any orthogonality, but that the edge set must be the same on all the layers, right? So this is a little bit restrictive, right? And I'm not saying that this works all the time, right? But if this is meaningful, like in the examples that I was showing, then this is really the crucial thing, because this is what in the learning step allows you this decoupling, because otherwise you would not be able to learn the signatures and the weight magnitude separately, right? So once you drop that constraint, then you're back to learning all the layers separately, which is more costly, of course. And then, as I said, in many cases, then there is an aggregation step that's required over the layers and so on. So this we can avoid by imposing this constraint. Okay, so if there's an edge, you see this here in the example for the Supreme Court, right? If there's an edge between two justices in layer 1, it must be there in layer 2. It can have another sign, right? And it does, right? So for instance, here, Rehnquist and Kennedy are both conservatives. So here there's a green edge between on layer 1, but on layer 2, they disagree on certain subjects. And this is expressed by the red edge on the second layer. But the edge is there.
Okay, so basically you don't, with this assumption, you don't have the flexibility of putting some edges to 0 in one layer and
Exactly.
with a sign. Okay.
Yeah.
I guess it gives you more interpretation if you impose that constraint.
That's what you give up, right? So it's a little bit more restrictive, but what you gain is that all this balance theory carries over and the algorithms become much more efficient.
Okay, thank you.
Yeah, so the talk was very interesting, so thank you. So my question is, so you mentioned that there are basically the graph signals that you're looking at are multi-dimensional graph signals. So every node actually has more than one dimension on it. So so what will be the physical interpretations of these different dimensions? So it seems that in the Supreme Court example, you do PCAs. But then what is the physical type of dimensions that you have in mind when modeling that?
Yeah, so I think that's related to what Gert was asking, right? In terms of what the meaning then of the individual dimensions is of the layers that you end up with, right? And so here in the example, it's pretty obvious that the first layer is just liberal conservative, right? But the second layer, I should have to look actually, right? Because there's some votes where O'Connor and Kennedy more or less defaulted and voted with the liberals, right? So you would have to look into what the precise votes were. Those are the ones that have large PCA weights, and then you could figure out what the social meaning of that would be, right? It could be that this is maybe some couple of votes related to the justice system or related to citizenship. So I don't know exactly. We didn't dig into the details yet, but you can trace it back to the original data, of course, right?
Yeah. So, well, another question is: so suppose that we really have the domain knowledge, so we know which dimension. So we know how to assign the different dimensions of the graph signals. So, what would be your ideal choice of the dimensions in these cases? So would there be some specific properties that you're looking at when you assign the signals to different layers?
Depends a lot on what you want to see. From a clustering perspective, the ideal choice would be to choose the dimension to be the log of k, the binary logarithm of the number of clusters that you're expecting. So if you have a data set and you expect, I don't know, 16 clusters, right? then you go for 4, then you go for 4 layers.
No, actually, my question was like by domain knowledge, like that would be something that you know what that fold is actually asking for example. So you're trying to fold, for example, in this data set. So suppose that you know what is actually behind that trend, what is being folded in each one of these 20 folds. So would it be able for us to exploit that domain knowledge, additional knowledge to actually construct your multi-dimensional graph signals?
So, yeah, I guess my answer here is similar to the question, to the answer that I gave to Gert's question, that if you have that kind of domain knowledge, it probably allows you to somehow bypass the PCA step, because the PCA is basically just blindly trying to figure out the 2 dominant components. If you have domain knowledge, then probably you may be able to do something smarter, depending on which measurements you deem more important or less important, and so on.
I see, but that measurement has to be somehow like something that can be dichotomized, something like that. You know, there's a liberal.
Yeah, exactly. Yeah. So that's the whole story, right? So if there is no dichotomies, then
I see.
I wouldn't advocate.
Got it. Thank you. Thanks a lot.
Okay, I don't see any more questions. There was a question about where to find more material about this. I guess, I mean, you have some papers on this, or can people find some material?
Yeah, so for the signed graphs, we had a paper in the Signal Processing magazine that can be easily found. The signature stuff is pretty recent, right? So this we just published at Asilomar last year, and then ICASP this year. Okay. So this is forthcoming, but I will be happy. Anybody who is interested, if you drop me an email, I will be happy to send out these papers.
Okay, perfect. If there are no more questions, then I think we can wrap it up here. So thanks again, Gerald, for the nice presentation.
My pleasure. Thanks again.
And then in 2 weeks, I guess, we have another presentation by Hao Zhu on applications of GSP and smart grid, I guess. So I hope to see you then. So have a nice 2 weeks.